Let's continue, take a look at the examples here. And before we really do some examples here, I want to first introduce an optional direction symbols for indicating torsion. The reason why is sometimes drawing circulations of a torsion symbol is confusing in certain conditions. So here I introduce a double arrow sign. Double arrow sign simply is to apply the right hand rule. You simply take your right hand and have 4 fingers pointing to where the circulation is. For example, you align your 4 fingers in this circulation, then you can find at this moment your thumb pointing to that direction. So that gives us the double arrow sign for this. Again, apply your right hand 4 fingers pointing to this circulation. In this case, you can see your right hand thumb pointing to this direction. So that is a double arrow direction for indicating this one. And you can exercise for this case. Basically, in here we will have a better, clearer indication that is very similar to force. Okay, and personally I like these symbols. Here I use double arrow simply is to indicate this is a quantity that is a moment or torque like quantity, and to distinguish the arrow, the single arrow that we've been used to indicate the force. Okay, and again, personally I like this double arrow signs, and probably from the lectures videos in classroom you will see my using double arrow sign here. Okay, so keep those kind of optional symbols. That will be additional for you to pick it up. And we can take a look at this example here and try to find the reactions and what is the torque in each of the segment here. Okay, so for this one, basically here we take the whole free body diagram, and you shouldn't assume the reaction at the wall here is 0. In general, it's not 0. So at the very first step, we need to find out what is the reaction force here. So let me pick the whole free body diagram of the shaft. Okay, and then here we pick is okay. So from here at this section here, that's a loading 11,000, and then here I apply the double arrow sign here. So let me change color here. So apply the right hand rule, and so on this case there we should see the loading is 11,000 applied here. Then the right hand rule here applied to here again, that's a loading. Sorry, the pen didn't listen to me well. So this is 7,000. Okay, and then apply this one again. Here is the loading applied 3,000. So from here to get in equilibrium, in total 14,000 pointing left in terms of double arrow and 7,000. So here we should have equilibrium. Here is 7,000 here. Okay, so starting from here, we begin to take the sections for free body diagram for each sections. The first one, let me pick a section here. Okay, so that's a section here. Then this is the 7,000 being translated from here. Okay, and now in this section you can see to make that equilibrium, this must be 7,000 pointing in that direction, double arrow sign here. Okay, so and here you can see it doesn't matter how you change the location of this cross section, as long as this section remain in this segment, the 7,000 always there. So here we can draw. So here I put the symbols for this one. Basically that's 7,000 in this way. So that's a 7,000 that's constant in the sections across the segment. So that's a 7,000 here. Okay. Then we can move on to the next one. So let me pick another cross section here. So let me pick this free body diagram. and to expose, including these sections I pick. Okay. So again, translated from information we have above, this is 7,000, and here is 11,000. So from here you can see get in equilibrium, this must be have 4,000 here. And again, this reaction 4,000 would be the same, doesn't matter how you pick the cross section as long as it remain in this section here. So that's a 4,000, and again this one alone to follow up this sign, and that should be above. Okay, so that is 4,000. So you can repeat the exercise, and let me do one more so for you. So pick this cross section. So in this way I pick these portions to save my time in writing. So here is 3,000 here, and again by action reaction this is in equilibrium, this should be 3,000 as well. And so again, depends, doesn't matter how you pick your location of the cross section as long as remain the cross section in between. So this 3,000 is constant, and again pick up this sign, and then that should be like this one. So now once you have all the things, then you can proceed to calculate, for example, phi equal to, say, our formula TL over GJ. And from here, for example, in segment CD here, then T equal to 3,000 you determined. The L is given here, G is supposed to be given, and J, and that you have information. For example, J for this segment is equal to pi over 2 c to the fourth power, so that's pi over 2 and 0.125 to the fourth. Okay, so a meter squared. So under this case, you should be able to calculate D relative to C here. Okay. And so that one, for example, if you'll be able to calculate, then you can see the T right now for this case is 3,000. 3,000 is in this sign. For example, if you really like, you can come up with a sign convention for yourself. You can say this is my negative and this is my positive. So under this situation, since you have assigned the sign to distinguish the quantities here, okay? So basically here, if you follow up your sign conventions, then you better to put a minus here, okay? And then we can continue to do our calculation. For example, relative, right now we into this, the BC segment, so C relative to B. Okay, and again, TL over GJ. And here you pick up whatever the information in portion BC here. Okay, repeat the similar process and then pick up right calculations. And again here, I want to focus on is here this T. What is T? T is 4,000, and right now you adopt your sign convention. So here should be 4,000 here. Okay, so here then the question is this, and what is the, for example, if you want to determine the relative, the angle of the twist between D and B, then for example D relative to B, then probably you can proceed is the D relative to C plus and C relative to B. Okay, and this quantities is determined by here, and this quantity basically intrinsically have some negative sign here because here you introduce this sign for your torque, and for this quantity is determined by this term here, and that basically intrinsically is positive. So whatever they come up with this sign, then you come up with the sign for the twist angle, and from there, and you further apply your right hand rule, you should be able to determine whether the relative angle, if you have a small guy and you have a small guy, if you sit here looking into the shaft, so the twist angle from this small guy's viewpoint could be from here if the numbers, and or that could be the angle could be go this way, that can be told by the sign here. Okay, so for example, if you come up with the sign is say the whole thing, if that would be negative, then you go to this viewpoint. If you go to this viewpoint, basically here when applying the the right hand rule, then that should be the circulation in this way. Okay, good. Let me repeat again. If you would say, for example, if this number, for example, let me make a one, say -1, okay, and then -1, basically here you can see the minus is according to your sign convention. So you are the small guy and sitting here because you see it is a minus sign, so you pick this viewpoint. And then right now you apply your right hand rule, align your thumb to the double arrow. Then your 4 other fingers pointing to is in this direction. So that is the way the calculated amount twist angle is in this way. Good. Okay. So here is the one example from our textbook. From our textbook, basically here we look at the problem statement here. We are given such a segment combined shaft, and then here let's have a different torsion applied to the pulley, and then we have the dimensions, we have a geometry, we have the rigidity. No, here we don't have that one, but that's okay. But here we want to determine the kind of design. We allowable stress is 65 MPa. So that means if here we have allowable 65, that means the whatever the maximum we come up with must be less than or equal to allowable to. That is our design rule from chapter 1 here, from chapter 1 before. Okay. So here we want to determine the minimum maximum shear stress in BC here, and we want to determine the diameter D in shaft AB. So we see how to approach this one. To stick with this this formula, so basically here we want to, first one is to find in shaft. We look at this one, shaft BC here, and we asking is the maximum less than or equal to 65 MPa. So that's our requirement. So what is a tau? We know the tau equal to TR over J. Okay, so therefore here we know the maximum is occurred at wherever the maximum R value could be. So here the R is basically here, this is the shaft of the BC. Okay, let me put that one here. So that is shaft BC, and that's a solid. And the solid basically that has the, this shaft BC is, let me see. The shaft BC is a solid, okay? So the shaft BC is solid, basically the radius C equal to 0.06 meter. So basically the maximum is happened at R equal to C, okay, so that is 0.06. So from these calculations then, and we should be able to proceed the calculations, okay? So from here you should be able to determine the maximum stress here, okay? And shaft BC is hollow, and let me, sorry, I didn't, the hollow inner radius outer, okay, so let me translate it. So let me redo this again. I think that's okay. For shaft BC, that is this, the outer radius equal to 0.06 meter. The inner radius equal to 0.045 meter. So here the maximum is occurred at the CO, okay, and the minimum occurred is at R equal to CI, okay, and then here the J equal to simply pi over 2 and CO to the fourth minus CI to the fourth. So with those kind of the TC and 0.045. Okay, so with those calculations, then you should be able to determine the remaining the calculations, the preceding remaining the calculation there. Okay, and here seems I have okay, so that's the thinking, and then one more thing. So right now we are able to determine the J, and here we identified R value for maximum, minimum, and what is T? So here that's a missing link here. Okay, so what is the T? So here we can repeat the same process. So let me translate the problem here. Okay, so that is a whole shaft, and here is A, and here is B, and here is C, here is D, and let me apply the loading and using right hand rule and apply to A here, so that is the 6. So using right hand rule, so that is the loading equal to 6, and apply right hand rule to B, and that loading equal to 20. Apply the loading to D, and that is loading equal to 26. Okay, and then here we have additional, so that is 20. So that's a 6 here. Okay, apply to here. Okay, so let's see if that be in equilibrium. Oh, here is 14. Sorry, apply the 14 here. So that is not 20, it's 14. Okay, that's the reason why. So right now you can see this is 6, 14, 6 to the right, 26 to the left. So this is good. So now we want to answer our question, what is the torsion in segment BC? Then again, you pick up the cross section here. Okay, so let me pick up the cross section here, and then this is a free body diagram. This is 6, and here is 14. So the reactions in BC here is how much? From here you can see that should be 20, and the unit is 20 kilonewton per meter. Okay, so again, this section doesn't matter how you pick in, as long as maintain between the ends of the BC, then that's always 20. So for this case, you simply plug in 20 kilonewtons meter. So everything is in place. In the similar process, you should be able to repeat the calculation for part B and refer to our textbook for details. Okay, so that is the calculations for netted. And this is a sample problems, and I leave this to you, and this is for hollow shaft, and that is very similar. Okay, that is basically repeated our detailed calculation for this one, for what the A here we provided. Okay, so that's a detailed calculation here. And this example is basically to exercise this formula here, and that one is to segment wise. And in particular, I use this example to again reinforce your concept of relative displacement or relative angle of the twist. Okay, and in general, if you like to say calculate the angle of the twist at A, you simply using this relativity, relative displacement A relative to B, B relative to C, C relative to D, and then D here. Okay, and here the D is fixed against the wall for this particular demonstration. So this one basically, this one equal to 0. Okay, so that reason why I didn't list in my kind of writing here. Okay, so on the other side, if you want to find the twist angle at B here, then you simply using this one, and again B relative to C, C relative to D, and plus D, and again D here is 0, so I didn't write it up. So something like this one. And what is this? That basically is our template, and you see this is in our generic templates. So for example, if we have a torsion here, okay, and then we know that V equal to TL over GJ, and whatever the segment here, for example, this is segment I, so whatever the information you pick it up pertaining to the segment I, you come up here. So A over B, this segment, basically you proceed the fundamental calculations like that one. And so what is this one? So this one, again, if you pick the segment BC here, so that is the segment BC, okay, and TL over GJ, in a similar way, you pick up whatever the segment BC, and then that is come up with this one here. Okay, so individual terms basically is the repeated exercise of our fundamental formulas for each segment there. Good? Okay. So that is the exercise so that is the detailed calculations. And again, for this case, pay attention to the minus sign here. Okay, why there's a minus sign? And again, that similar to our previous example here. Let me show that one here. Okay, so that is similar to here, because when you decompose, taking the cross sections, then you will find the sign follow up this kind of right hand rule, then the positive or negative that is coming due to this reason. So you can repeat this exercise and to here. Okay, so that's the reason why we have a minus sign here. And based upon your sign convention, it might be for some of you, your minus sign will appear here. So, and the two terms will be positive. Really depends on how you define your sign convention. Okay, so for some people, based upon your selection of a sign, then your negative sign could be appearing here rather than the two term here, but that's okay. And then once you have those things, then for example, the A relative to C, for example, if I want to find out the relative angle of the twist between the two ends, A and C here, then simply proceed this calculation and something like this one. Okay. And this is the another example here. So for this case, we want to determine the largest torque that can be applied. And again, this is to fit into the design problems, because here we are given the allowable stress. And so that means allowable stress, that means the maximum must be less than or equal to the allowable. So that is our golden rule. Okay, so for shaft BC, so let me change. So that is the in shaft AB. Okay. So in shaft AB, basically here, if we take the free body diagram of the AB here, then you can see again using our right hand rule. So that is the torque T applied, and reaction to the torque T applied. So basically this is a solid. So the maximum in shaft AB equal to T TC over JC, TR over J, and here the R is the radius, okay, and 0.75 inch, okay, and J basically the R and J equal to pi over 2 and 0.75 to the fourth power, okay. And so from here you should be able to determine, plug into here, the T must be less than or equal to 9.94 the KIP inch. And what is KIP inch? KIP means the 1,000 pounds. Okay, 1 KIP equal to 1,000 pounds. And now we proceed the calculation for shaft BC. So that means the maximum in BC must be less than or equal to the allowable. Allowable is how much? Allowable is 8. Okay. Oh, what is KSI? 1 KSI equal to 1,000 PSI. And what is PSI? PSI is pound per inch square. Okay, so that's our unit. So what is maximum BC here? So for maximum BC is okay, the formula is TC over J. The formula is TR over J, and for the maximum happened at R equal to the outer radius. So that is the outer radius here, and that is 0.9. Okay, the diameter is and then what is J? J equal to pi over 2, and because C is the solid, so that is the 0.9 to the fourth power. So plug in here, you can see basically here that one T must be less than or equal to 9.16 and KIP inch. So now we have two values, and from to satisfy the design criteria for shaft AB, the torque must be less than 9.94. To satisfy the design criteria for BC, torque must be less than 9.16. For this problem, we want to satisfy both. So that means checking the both conditions, then to satisfy the both, t must be picking up the smaller number, so the 1.96. Because under this case, when t less than this one, then definitely BC will be satisfied, this kind of the allowable. Then when this number plug into portion BC, because definitely this will be less than allowable. Okay, so that is for this province.